Hi physics friends, in this screencast I'm going to take you through how to do the analysis for the vector walk lab. If you're in honors physics, please make sure to record the two learning targets on your target tally sheets, and let's get right to it. For this lab I worked with Mr. Medic, this is Mr. Zarzek by the way, and we decided to start our trip down by the old physics rooms, which used to be rooms 317, 316, and 315. Honors was in 317 and Reg was in 315 and 316. We decided to go down the hallway towards the auditorium, which is south. Okay, then we made a left-hand turn, which if that is south, that means we went east. And then we turned south again to go visit Mr. Stacy in the Merc. Vectors are just arrows, and so we draw an arrow to represent our displacement first traveling south. And then a second vector lined up tip to tail. See, the tip of the south vector lines up with the tail of the east vector. And then finally a third vector that goes south, once again lined up tip to tail. Your trip may have had more than 2 turns, but that's the minimum criteria for the lab, so that's what we'll be using here. Now, it's not necessary to draw the vectors on the map that you were given. It's necessary to diagram that, and for that you'll need to scale your diagram. When you scale your diagram, bigger is better. In other words, much like when you're making a graph, and well, this is really a vector graph, you want to scale it so that your vectors take up as much as your paper as possible. So choose a scale that fills up the majority of the paper. Draw your arrows, or excuse me, draw your vectors. Make sure to turn them into arrows so that they become vectors. And then label those vectors as displacement. You'll be using centimeters in your big paper, but they represent meters out in the hallway, so label them as such. Also make sure that you put whatever scale you're using right on the paper as well. And note that each one of these vectors is drawn tip to tail. So the tail of the 10-meter vector lines up with the tip of the 8-meter and so on. The blue line that I've added in represents the resultant of adding these 3 vectors together. This resultant vector is for displacement. This is your displacement, or the distance from where you started your trip straight to where you ended. Pay special attention to where you put the arrowhead on the resultant. And remember from class, when we draw resultant vectors are drawn from where we started pointing to where we finished. So it's kind of opposite of what we did with the component vectors. The goal of the lab is to determine that displacement vector from 2 methods. The first is that, well, you've created a scale diagram using a meter stick to map out meters in the hallway to centimeters on the paper. Well, now you're going to work the other direction. Measure the length of this line using a meter stick, record the value in centimeters, and then use your own scale to convert that value into meters. Remember that factor unit label method is required, so you can just kind of follow the example I've laid out for you here. You want to show that conversion right on the paper. In fact, the big butcher paper is going to be what you'll be turning in for your lab team. Once you've made that conversion, record the resultant vector right on the displacement vector on your big diagram for this value that you've now determined through making a measurement. Now, how do we know if our resultant is correct? I mean, we can't exactly go poking holes in walls to run tape measures. Okay, and so to build confidence in what we measured using our own scale, we're going to try to verify this value using the Pythagorean theorem, which is the rule that we use for right triangles, which means that we need to turn this vector diagram into a right triangle. To do this, we're going to take advantage of the commutative property of vector addition. The commutative property of addition and vector addition work essentially the same way, and all it says is that the order in which you add things together doesn't really matter. So think, at some point during the trip we walked 10 meters, and on my diagram it was to the south, and then some point later we walked another 7 meters to the south. In between we went 8 meters. Well, what if the path was available to us? In other words, what if we could walk 10 meters to the south and then right away go another 7 meters? Our overall displacement to the south is just 17 meters, the sum of those 2 components. In which case, what we're really doing here is just changing the order in which we're adding our component vectors to turn it into something that's more convenient for us. Just so you can see it, here I've rearranged my components to add the 8 meters to the east before the 10 meters and the 7 meters to the south, and we still wind up with the component vectors pointing right to the same location, where the arrow tip for our resultant vector is sitting. We can think of the 10 meter and the 7 meter just as the 2 components that point along the north-south dimension, And so when I put them together, they're exactly the same as one single displacement vector that goes 17 meters straight to the south. Since I've now created a right triangle, well, I know how to deal with right triangles. If I have two sides, I can then calculate the hypotenuse. Now, of course, in this screencast, I've made a really pretty diagram that's idealized, and so when you take 17 squared plus 8 squared, and then you take the square root, you'll get 18.8 meters. However, in the lab, we always expect to get a little bit of error, and that's okay. What we're really looking for to determine a successful lab is that resultant close to whatever we did using our meter stick and then converting using our scale. In the honors physics version of the lab, we're also going to have you make a measurement of the angle of the vector. The angle of the resultant should be from in between where you started for that first vector and the resultant that you drew. So what I'm getting at is we took this vector diagram, okay, and we worked with it as if it was a right triangle that looked like this. Okay, and so what we're going to do is we're going to make a measurement of this angle. This is an acute angle. This will be somewhere between 0 and 90 degrees. Okay, protractors are located in the cart in the front of the room, right by the rulers and the meter stick. So grab a protractor and make a measurement of this angle. This angle represents the direction of the resultant. So think, when it comes to vectors, vectors are described by two numbers: the magnitude, which is the 18.8 meters, and then the angle, whatever we happen to measure. Much like we can measure the magnitude of the resultant using a meter stick and then convert, and then compare that to what we can calculate with Pythagorean theorem, okay, we're going to do the same basic approach with the direction. I'm going to measure that direction using a protractor right on my big paper, and then I'm going to use the lengths of my triangle to actually calculate that angle. Okay, and so just so you can see it, okay, I know this kind of got cut off here a little bit, but this was the 10 meter vector, and then this was the 7 meter vector, which gave us an overall length of 17 meters along the direction south. And then just using that commutative property rule, okay, I put the 8 meter vector up here, all right, like that. So I've got my right triangle, which I know it got cut off a little bit here, sorry about that. Okay, and then so just using trigonometry, all right, well, if this is the angle that I measured, okay, well then this 8 meter vector over here, that's on the opposite end of the triangle as where I made the angle measurement, so that's the opposite side. And then this length here, which is right next to the angle, that's the adjacent piece, so the 17 meters is the adjacent part of the triangle. And so I use the inverse tan function to calculate an ideal for what that angle should be. The final part of the lab asks you to perform the statistical analysis of the error. For this case, we're going to use the percent difference formula. In physics, we're using one of two error formulas, either the percent error formula or the percent difference formula. Why do we have these two? When do we know what to pick and why to pick it? Well, if we're going to use percent error, that would be when we are comparing something we do in the lab to an accepted value. So think like in the bouncing ball lab, we tried to measure the acceleration due to gravity. And well, we know that the acceleration due to gravity is 9.8 meters per second squared down. Okay, well, when we actually measured it in the lab, many of us got something a little bit different because they're air resistance. Likewise, in the reg version of the lab called bleacher bum, we dropped things from the bleachers and tried to calculate the acceleration of gravity and found something that was a little bit different than 9.8. That's when we use percent error. In this lab, we use percent difference because, well, both the measured value that we got with the meter stick using conversion and the calculated value that we use with Pythagorean theorem, okay, those are both experimentally determined. The same as can be said for the angle. Okay, we measured the angle with a protractor and then we calculated it using trigonometry. All right, neither of those things is any more correct or incorrect than the other. What we're really trying to do is compare the two methods. The idea being that if we can arrive at the same result from two different approaches, that's good evidence that our prediction, which for this lab is what's the displacement, is a good one. So that's the idea. Okay, this is another method in which we apply to do science. Thanks for listening. Good luck with the rest of your lab. We'll see you in class.